Hello. The rise of deep learning plays a crucial role in applications like image classification, object detection, and semantic segmentation. Can these perception-based neural networks assist the controller in the feedback-based controller system? If so, is such kind of a system is safe? In our research, we try to answer those kind of questions. This research is conducted by me, Dr. Bradley, and Professor Wolf from University of Nebraska-Lincoln, and Dr. Johnson from Vanderbilt University. The major contribution of this work includes using a novel simulator to incorporate the LEC components in the unmanned aerial systems and implementing a neural network-based perception system which can assist the controller in a closed-loop system, and also trying to applying the ALC and NNV toolchain to verify those kind of neural networks. We conducted our experiment in an airsim simulator, and ROS is used to control the unmanned aerial system, aka the drone. The experiment scenario includes two drones, the target, which follows its trajectory. We designed an S-shaped trajectory because an S-shaped trajectory is going to have varying velocities in both directions. The chasing drone needs to detect the target and follow it by using the perception neural networks and feedback controller. You can see the sample architecture of the system here. The chasing drone obtains the image and which is fed into the convolution neural network, through which it gets the image coordinates, which will be used to convert into the simulated world coordinates of the target drone. These will be set as a reference to our feedback controllers, which are PID controller in this case. And these PIDs guide the chasing drone to follow the target drone. There is always a trade-off with the convolution neural networks. Some networks are very fast, but not accurate enough, while the others are very, very accurate, but not fast. That is the reason why we choose two neural networks. One is the fast RCNN and another one is the SSD. The fast RCNN is well known for its high accuracy, but it can run slower inferences only. Whereas the SSD, it can run faster inferences, but it is not as accurate as fast RCNN. We trained both of these networks using a data set which contained 300 images which were created and labeled by us. You can see a sample results of the detection here from a frame obtained by the chasing drone. Through this, the chasing drone able to detect the target in the image. But to be able to follow the target, the chasing drone needs to know the location of the target in the world coordinates. For that, we use an image coordinates to the world coordinate conversion, which you can see here. The width center of the bounding box and the height center of the bounding box contribute towards the changes of the target drone along the y-axis, which is the left and right axis, and z-axis, which is the top and down axis. And the area approach helps us to get the coordinates of the x-axis, which is the front and back axis. And once these coordinates are obtained, an error will be calculated, and the velocities will be generated using a PID-based controller, which you could see here in the matrices. And you can see a sample video demonstration of chasing drone chasing the target in this video. Here you could see the detection based on using the neural networks. The detection is so robust that it can detect the drone even in the black background. Here you could see the chasing drone trying to chase the target drone. And you could see the chasing drone's point of view in here in the frame. And this is the ground view. That is the end of the video demonstration. You can see some sample results here. We tested this trajectory with various velocities such as 1 meter per second, 2 meter per second, 5 meter per second, and 10 meter per second. And the RCNN, it can run at most of 3 edges, which means 3 influences per second. So we use 1 Hz, 2 Hz, and 3 Hz operational frequency. And the SSD can run at most of 30 Hz, so we use 5 Hz, 10 Hz, 20 Hz, and 30 Hz frequencies. Here you could see the results of RCNN. The 1 Hz based frequency, it started filing from the beginning onwards. The 2 Hz, it's able to chase the target until the middle of the trajectory, but it lost at some point when it's near to the middle. And the 3 Hz based operational frequency, through that it's able to chase the target almost until the end of the trajectory, but it lost before the end of the cycle. Through which we can see that as the operational frequency increases, the system is able to perform well. And the SSD plot reveals the sequel of this story, which is the 5 Hz here is able to track the target until the end of the trajectory. 10 Hz also tracked the target until the end of the trajectory, and it did better than the 5 Hz, which is anticipated. But from 20 Hz and 30 Hz onwards, even though the operational frequency increases, the system performance stays still, which tells us that there is a saturation point upon which even the frequency increases, the system performance stays there. The overall result of RCNN can be seen in the table here. The average velocities are shown in the column and the frequencies are shown in the row. The average error for each trajectory upon the end of the trajectory is calculated, and which you can see here. And from 5 meters per second onwards, the RCNN starts filing, and there are no errors in the case. The similar results for the SSDs can be seen in this table, with the 5 different velocities and 4 different frequencies. The average errors for each trajectory is calculated upon the end of the trajectory. In the SSD case, it started filing from 8 meters per second onwards, few frequencies able to do, for which the errors are noted down here. There exists ALC and NNV toolchain to verify the convolution neural networks for the task of image classification. But for the convolution neural networks of object detection and localization, there is still an active research is going on to find the best NNV methods. Moreover, there is also a challenging to apply these methods to convolution neural networks of object detection, since they are very dense, which falls under the class of NP-complete, which means it is computationally very expensive. The results depicts that the neural network-based perception and feedback-based controllers could be co-designed for a better results. And to making it seem to real, the biggest problem would be latency on low power boards. Hardware logic synthesis could help by a bit to alleviate this problem. Moreover, a neural network verification method is needed to verify object detection and localization based convolution neural network. In conclusion, this work presents using a novel simulator to enable LEEC components in the drones and implementing a perception-based neural network and tight coupling those with a feedback-based controller system, and stating the need of a neural network verification method to verify the object detection and localization-based convolution neural network. If you have any questions about this work, please send an email to us, and we are happy to answer. Thank you.